Hello, everyone. First, I would like to thank the organizers for the invitation. I'm very happy to be here to share with you some of our recent experience in building the world's largest AI marketplace for ride-sharing. DiDi is the leading ride-sharing platform in the world. We have over 550 million users, and we complete about 10 billion trips every year. We provide one-stop multi-mode transportation services, including premium, express, taxi, carpooling, bike sharing, etc. Globalization is a core strategy of DiDi. Besides China, we have launched services in many other countries, including Brazil, Mexico, Japan, Australia, etc. DiDi is also the largest transportation data company. We generate about 100 terabytes of data every day. Every vehicle in our platform sends back GPS signal every few seconds. Our trip data is not only big, but also complete. Using Beijing as an example, if we combine all trip data in Beijing in one day, we can cover almost all roads in Beijing for about 400 times. We are thus in a unique position to mine knowledge from such a huge amount of trip data to enhance travel safety, convenience, and efficiency. In the course of the journey, we have witnessed how technology has transformed the transportation. Looking into the future, we believe the transformation will happen at 3 levels. The bottom layer is the transportation infrastructure. The infrastructure will become smarter and smarter in the future, including smart road networks, intelligent traffic signal control, and smart parking. The middle layer is the vehicles. Electric vehicles and autonomous vehicles will gradually replace the traditional vehicles in the next 5 to 10 years. The top layer is the shared mobility. In the future, people prefer not to own a vehicle, but share a vehicle with others. Some study has analyzed data in New York and found that only 1/3 of the vehicles are sufficient to satisfy all demands. This will greatly reduce the number of vehicles on the road, reduce the traffic congestion, and reduce the pollution. You can see in all 3 layers, AI plays a very important role. Thus, the strategy in DiDi is AI for transportation. AI has been used extensively at DiDi platform, including smart transportation, smart vehicles, intelligent operations, such as dispatching, supply-demand forecasting, and carpooling, mapping, including traffic prediction, route planning, and travel time estimation. Customer service. Each day we receive millions of calls from our customers. We have built an intelligent customer service using NLP, speech, and knowledge graph. Many of the calls can be answered now automatically by machines. And this greatly reduces the cost. Safety is our top priority. We have built a system based on computer vision, speech, technology to enhance safety. We have also launched AI for social good platform for better health, environment, and safety. One major challenge in DiDi marketplace is supply and demand imbalance. This figure shows a snapshot of the supply-demand situation in Beijing. Here, a large negative number in a red area indicates there are more requests than drivers, while a large positive number in a green area indicates there are more drivers than needed. We can see at every moment, there are a large number of red areas and a large number of green areas. Such imbalance significantly affects the efficiency of the system. How to balance the supply and demand is a major challenge in DD platform. A variety of different strategies have been developed in the past to deal with such challenges, such as dispatching, repositioning, surge pricing, incentive design, driver assistance, etc. We will discuss some of these strategies in this talk. First, dispatching. Dispatching is one of the core components of DD platform. We perform dispatch in every 2 seconds. First, we collect all drivers and passengers within these 2 seconds in the form of bipartite graph. Then we assign a score to each pair of driver passenger. The score indicates the matching quality of the pair. That is, a higher score means a better match. Intuitively, a large driver distance and a long travel time indicate a better match. All these scores then form a score matrix. The rows correspond to drivers and the columns correspond to passengers. Then standard bipartite graph matching algorithms, such as the KN algorithm, can be applied to find the optimal match. Here, optimal means the maximum number of passengers within these 2 seconds got matched. Dispatching involves 2 key mapping operations, including route planning and travel time estimation. Here, ETA means the estimation of the traveling time and the waiting time of each ride. The estimation is quite challenging since we need to estimate traffic condition of each road segment in the future. Besides, each traffic light may make a big difference in travel time estimation, and each trip may include multiple traffic lights. We have developed a wide, deep, and a recurrent model for ETA. We model each route as a sequence of road segments and apply LSTM to model the sequence. The system achieves state-of-the-art performance and has been deployed online to serve billions of ETA requests every day. Here is a demo.
City moves. Time flies. People get around cities. We rush from one place to another. Inaccurate route and long wait time affect your trip experience. KDD'20 has provided 550 million users with 7.43 billion trips in 2017 across the world. We are tackling the global problems to bring you reliable transportation options and to meet your diverse needs. DD AI Labs has initiated a deep learning-based mapping system. Through neural networks and reinforcement learning, the system provides a better route planning and a more accurate ETA. The new system is more accurate and faster with less computational resources. It delivers stable services even when there's a huge amount of on-demand ride requests. It enables us to send an accurate real-time dispatch in various changing transportation conditions. When DD users are on the way, the system makes a huge amount of real-time calculations to respond to dynamic traffic changes and on-demand ride-sharing requests. It also takes other factors into account, such as rider and driver location, traffic status, trip data, driving behaviors, road networks, and driver ratings. By doing so, we can dynamically dispatch trips and plan routes in the most optimal way. The core algorithms in this mapping system are much more accurate, but require less computational resources. The mean absolute percentage error, MAPE, has decreased to 12%. The time for calculating ETA has decreased to 20 microseconds. And the number of requests per second the servers can handle has increased by hundreds of times, meeting the demanding requirements of different scenarios. Devoted and wholehearted, DD uses intelligent algorithms to redefine the mobility industry. Better route planning and shorter wait time make your trip experience more reliable from one place to another and from present to future. DD is always dedicated to a better journey.
Every dispatching decision affects future supply distribution. For example, a driver matched with a passenger will move to the passenger's destination after the trip is completed. Thus, we can model dispatching as a sequential decision-making problem and apply reinforced learning to solve the problem. The goal is to maximize the long-term reward instead of the short-term reward. Here, each agent is a driver. The state includes time and the location. The action includes a match with a passenger or no match. The reward is driver's income if there's a match, or zero if there's no match. And each episode is one whole day. The value function estimates the expected future income of a driver in a particular state. Such value function can be extremely useful for drivers to make decisions on where they should go next. For example, in the morning, most high-level areas are along the suburb area, while in the afternoon, most high-value areas are located at the central area of the city. We have deployed our NDP-based dispatching system online since 2017 and served top 20 cities in China. The driver's income was increased significantly, while the user experience is not much affected. The NDP-based model is simple and effective, but it has several limitations. First, the state space is very simple, including just that time and the location. Several other features, including real-time supply and demand information, are very relevant, but not included in a calendar model. For example, when it rains, then the supply demand will be very different and should be captured. In addition, we learn a value function for each city separately. It's time consuming since we have hundreds of cities, and also the learning for small cities is challenging. To tackle these challenges, we have developed VNet, a deep value network-based approach for dispatching, which directly approximates the long-term value of a spatial temporal state. The network can easily incorporate contextual features such as weather, dates, real-time supplies and demands, etc. Since it's a network-based approach, the knowledge from one city can be easily transferred to other cities. Like deep Q network, the learning of VNet may not be robust. We apply Lipschitz regularization for robust learning with nonlinear functional approximation. In addition, we apply a hierarchical representation of the spatial space, since the object of interest may be of different sizes. More details can be found in our KDD'19 paper. We perform a simulation study and compare VNet with 5 different methods, including KN and DQN. We can observe from the figures that VNet achieve significant improvement over the others. And interestingly, the use of transfer learning across cities can further improve the performance, and sometimes by a larger margin. These 2 figures show the value function of one city at 2 different time points. We can see, unlike the morning rush hours, the area of high values during the afternoon rush hours, mostly located at the center of the city. This is intuitive as many people return home from the office in the afternoon. We also perform A/B testing on 3 cities, Wuhan, Dalian, and Nantong. The overall sample size exceeds 10 million. We compare different methods in terms of driver income, finish rate, and answer rate. We can observe from the figure that VNet significantly improves driver total income, as well as user experience and platform efficiency. Our work on reinforced learning-based approach for ride-hailing order dispatching won the 2019 Wagner Prize from Informs. It is one of the top awards in operation research practice. Last year, 5 teams were selected and competed in the final stage, including Harvard, Columbia, Georgia Tech, University of College London, and DD. We won the first prize due to the technical innovation and the practical significance of our approach. Repositioning is a very popular approach for tackling the supply-demand imbalance problem. The key is to accurately predict future supply and demand. The figure shows real-time supply and demand information in a region. As we mentioned earlier, a red region means we are shortage of supplies, and a green region means we have more drivers than needed. If we can predict the supply demand in advance, we can dispatch vehicles from green regions to red regions with high demands. This can significantly improve the efficiency of the system. We have developed a spatial-temporal multi-graph convolutional network for demand forecasting. It applies LSTM to model the temporal information and a graph convolution to model the spatial information. LSTM and graph convolution are now very popular tools to model spatial temporal data. More details can be found in our AAAI 19 paper. I want to mention a key novelty is the generation of multiple graphs, modeling the spatial dependency between different regions. We generate 3 different types of dependency. Region 1, region 2 are spatially close to each other. They form the first type of dependency. This is quite intuitive. Region 1 and region 3, they are very far away from each other spatially, but they share similar POIs. They form the second type of dependency. For example, if both regions are universities or hospitals, they likely share similar demand patterns. The third type of dependency is a surprise to us. It's between region 1 and region 4. They have a direct road connectivity. For example, there's a highway connecting these 2 regions, although they are quite far away from each other. We have compared our approach, spatial temporal multi-graph convolution, with other approaches. Our extensive experiments in 2 cities, Beijing and Shanghai, show the proposed approach significantly outperform existing approaches. And our results also show all 3 types of dependency of graphs play very important roles in the prediction. We have recently developed a driver assistant to further help drivers increase their incomes. The system will tell drivers where they should go when idling. Such system is especially useful for new drivers. The key is to reposition drivers to areas with high long-term values. We estimate such value based on VNet. We have done a simulation study. Our results show that the proposed system significantly improves the performance, and the driver's income is increased significantly. And we recently finished an online A/B testing. We picked 500 drivers from 2 cities. In China, our results show that our system can increase the driver's income and reduce idling time significantly. We plan to do the next experiment in mid-August by involving more drivers. The goal is next year, we'll pick a city where all drivers are equipped with our assistant. This will show the full potential of AI, enhancing the system, efficiency of the system. Here's a demo.
The AI assistant for drivers innovatively applies ED's deep reinforcement learning technology to driver dispatching, while optimizing user experience and improving marketplace efficiency. It increases drivers' income by guiding them to make smart decisions. Based on deep reinforcement learning and decision theory, AI Assistant utilizes spatial temporal dynamics and deep neural networks for long-term value estimation, providing precise and effective dispatching guidance to the drivers.
CBD is now very busy. Do you want to go there? You may answer yes or no.
Yes.
Navigation start.
AI Assistant also maximizes the chance of the driver getting matched to a trip request, reducing vacant hours. Upon arrival at the dispatching destination, the driver stands by briefly as requests are automatically matched by the platform. Xiaodi, please call the rider.
Okay, calling the rider.
When the trip is completed, the driver may disable AI Assistant or accept the next task. A break reminder would be given based on service time, billing hour, and opportunity cost. This feature improves road safety and drivers' income at the same time. AI Assistant empowers drivers on the platform to efficiently facilitate urban mobility and satisfy riders' needs. It optimizes the spatiotemporal distribution of supply and demand, enhancing service efficiency and social welfare.
In this talk, I share with you some of the major challenges in Ridesharing marketplace and present some of our recent work on how to build an intelligent Ridesharing marketplace. So far, we optimize each component, such as dispatching, repositioning, driver assistant, incentive design, pricing, separately. I think an important future direction is to build a joint framework to optimize multiple components simultaneously. In the last 20 years, internet has solved the problem of moving information around the world. Today, DD wants to solve the problem of moving physical things around. The transportation industry is still at the nascent stage. DD is still a young company. You only have to look out of the window to see how much room there is for improvement. DD is trying to be a front runner to push the frontier for future transportation. We hope all of you will join us on this journey and look forward to working together towards the better future. Thank you.